We'll go small for a second. We'll stretch it out. We're about a quarter of the way through this section, or through my speaking portion. I feel pretty good, maybe as we're in this sort of intermediate part. We'll do a graph of how I expect this to go. I have a lot of graphs in this. So here, this is going to be the time elapsed, and this will be how deranged this is. This is. Okay? And then my expectation is that we're going to be sort of around here for a while. This is sort of the first section. We're getting increasingly more deranged. And then 5-minute break. 5-minute break. Then we'll start off a little bit less deranged. And then we'll spike again right at the end.
And then that'll be 6 hours.
And that'll be 6 hours. 6 hours. Okay. But we're not there yet. We are, I think we are here. You are here. So this ride is just getting bumpier as we go. Cool. Questions on the graph?
Questions on the graph.
Is this continuous? No, there's a 5-minute break. That is a good question, though, yes. There is a hole of sorts. Okay. So we'll do the whole picture. All right.
Are you guys going to sleep through, like, are any of you sleeping throughout this entire thing? Are you guys all staying up for 24 hours?
No sleep. No sleep. 24 hours. Keep her going. All right. We're back. We're pressing buttons again. We'll make this bigger. We're going to start off like with a pretty straightforward problem that you might have seen before. We'll figure out if we can solve it. This is going to be sort of like the sock problem of the last one. So we have 14 students in a discrete math class. We have 12 students in a linear algebra class. More students are taking discrete math. I set that up perfectly because I wanted it to be more popular. So 6 students are going to be in both classes. I want to ask how many students are in both classes combined. So the idea is I have 14 in discrete math. 14 in discrete math. $12 in linear algebra. Okay, I'm going to do something wrong, and you guys are going to tell me what I did wrong. So the idea is the total number of people in both classes should be total equals 14 plus 12 equals 26. No, you say, that's wrong. Why is this wrong? Yeah, I've double counted the students in both classes here, right? There are 14 in this class and 12 in here, but it's not 26 total because some people are in both classes. So the idea is, make a note, wrong, so foolish of me, wrong, 6 people are in both classes, and they have been counted twice. Have been counted twice. Okay, so I have my number 14 plus 12. What do I do to fix this number? How do I fix? I've double counted 6 people. What do I do? Subtract, yeah. I'm going to subtract off 6 right here. So this is the total, but minus the number of people that I double counted, because I double counted them because they were in both of these sections. So this is, right, this is the people in discrete math. This is the people in LA, linear algebra, minus the people in both. Should equal the total, which is 20. Total. Okay. So this will lead us to what we call the inclusion-exclusion principle, which I'll show on the next page. So here the theorem states that we have, well, I'll just go over this. I don't think we need to go over this notation too much. I'll just do it with the picture, sort of what's going on with this. You might remember these vertical bars from earlier, which talked about the size of something. That's still what we have going on right here. We think about A and B as being sets. I'm just going to draw a picture. Here, maybe over here. This is a Venn diagram. Maybe this is the section A. This is the section B. And some colors. Let me know if the blue shows. I'm going to shade. It doesn't. Okay. In green, I'm going to shade red. Hopefully no one's red-green colorblind. This is sort of what I wanted to avoid. And in red, I'm going to shade section B. Okay. So we'll label this that. Everything shaded red represents all of B. It measures how big B is. The area that's red measures the size of B. Everything shaded green talks about the size of A. However much area is shaded green is the size of A. And then, so this notation right here is just asking what area is shaded red or green. Red or green, and then in math, or means or both. So red or green or both. Okay, so that'd be red or green or both. Thank you. Thank you very much, Linda. Okay, so this is the area that's red or green. The next piece of information, I'll make it big, will be the last one, which has the frowny face between the A or the B, or the cap, I suppose we call it in math, which is the area that's both red and green. Oops. That was unfortunate. We'll move on. We'll battle through. Red and green is the area. That's both. Yeah, we just moved up in how deranged this talk was. That was just a taste. For me, it was especially a taste. Okay, so here, and in this, notice, again, this is the area that's shaded both red and green. So what is this sort of depicting with this notion is the idea is, what's the area that's shaded red or green? You take the area that's shaded red and the area that's shaded green. You add those together, but you've double added the area that's shaded by both colors, so we're going to subtract that off one time. It gets counted twice, so subtracting it once gives it one total contribution, is this idea of inclusion-exclusion, sort of at this first level. Okay, questions on this so far? People feel good? Green's kind of showing up. Nice. Okay. We'll go to the next thing. Leave this up. So our problem will be to find the number of positive integers that are smaller than 100 and not divisible, bless you. Thank you. You're welcome, by 5 or 7. Okay. So for a lot of these problems in this next section on inclusion-exclusion, we're going to use the subtraction principle that Ryan graciously provided us with earlier on. So we're often going to be looking at a universe, all of the ways to do something, and we're going to subtract off the bad things, the things that don't do what we want, and then we're going to use the inclusion-exclusion principle on the bad things. This is also a thing, perhaps this was discussed earlier when I was at a fugue state, but oftentimes in math, it's easier to count all the things and then remove the bad stuff than it is to count the good stuff. which is maybe a pessimistic viewpoint, but that's just, I guess it's easier that way sometimes. All right. So my first question is, how many positive integers are there that are less than 100? And I will wait for an answer. How many pos ints less than 100? 99. 1, 2, 3, 4, or yeah, all the way up to 99. Numbers that are 1, 2, 3, up to 99. Yeah, so there's 99 of them. Okay, so that's all of our stuff going on. Okay, so the next question is, how many positive integers are less than 100 and divisible by 5? So I'm going to think about it now. I'm going to use my A and my B. A is going to be set of positive integers less than 100, and divisible by 5. By 5. We can list them because I have pretty much infinite time here. So what are these numbers? So this is, well, 5 is divisible by 5. 5 equals 5 times 1. And you have 10, 5 times 2, 15, 20, 25, 30, 35, 40, 45, 50, 55, 60, 65, 70, 75, 80, 85, 90. 95, thank you. I'm keeping you on your toes, you're welcome. 95, but notably not 100 because 100 is more than 99. So we're looking at things that are divisible by 5, and we stop when we get to 99. Okay. Our next question is, what is the size of A? This set. So how many elements are in this set? We can count them, I'm just going to do that right now. This is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Okay, so there's 19 elements in here. Why is that? This is 5 times 1, 5 times 2, 5 times 3, 5 times 4, 5 times 5, all the way up to 5 times 19. You can see each of these. And you'll notice that, so this is equal to 19. Also notice that what is 99 over 5? Does anyone know? It's very close to 19. This is actually going to be 19.8. Okay? So this is no coincidence. I'm not going to necessarily justify this, but yeah, I encourage you to think about this on your own. The size of A is going to be equal to the biggest integer smaller than 99 over 5. And if B equals the set of positive integers less than 100 and divisible by 7, by 7, you end up again finding that the size of B will end up being the biggest integer smaller than 99 over 7. Does anyone know what that is off the top of their head?
And I want to make sure, like, if say if your large number was 100, 20 would be the number on the right, but what you're saying right now would be less than or equal to that. Yeah, that is a very good point. So if this was 20, I wouldn't be looking at 19, I would just be looking at the 4. This is technically, if people have heard of this before, we're looking at the floor function. So if you look at the floor function of like some number x equals smallest integer less than or equal to x equal to x. Largest, yep.
We're getting there. Largest integer. Okay, cool. And there's a corresponding thing about ceilings, but we're not there yet. Maybe we'll never get there with me at the helm. All right, so the size of b will be given by the floor of 99 over 7. So again, this is the biggest number that I can multiply 7 by and not get above 99. It sort of makes sense for us. This ends up being 14. 14 times 7 is 98. So this ends up being 14. Okay? What's going on with this? Okay, so I have this written down. I'm going to specifically remember like what I know what A and B are. I know the size of A, I know the size of B. To use inclusion-exclusion though, I have to figure out, right, so I can add the size of A and B, but I've double counted numbers that are divisible by 5 and 7. So in terms of the bad numbers, I need to subtract, or I need to subtract what their intersection is to figure out the total number of bad numbers. So what is, the idea is the intersection of A and B means numbers that are divisible by both 5 and 7. So A union B is the set of positive integers, pos ints, less than 100 and divisible by 5 and 7. So if you're divisible by both 5 and 7, you're divisible by the product of 5 and 7 because 5 and 7 are prime numbers. So divisible by 5 times 7, which is 35. So the size of this thing, size of this bad Larry, is going to be 99 over 5 times 7. So we're looking for, what's the biggest number I can multiply 35 by and still be less than 99? It ends up being 2, because 3 times 35 is 105, which is too much. So this ends up being 2. So if I want to take all these pieces together, I have my universe right here, 99, and I want to subtract the size of A plus the size of B minus the size of the intersection. So I'll do that right here. The total should be, I'll do some erasing. I guess we'll do it up here. Total equals 99 minus size of A plus size of B minus size of the intersection of A and B to account for our double count. Translating this, my friends, this will be 99 minus 19 plus 14 minus 2. Cool. Minus 2, which is 19 plus 14 is 33, minus 2 is 31, so the total is 68. Cool. Questions on this? No? Feel good? Very good. All right.
What if you did the number of positive integers that are no more than 100?
No more than 100? As it turns out, the answer will be the same.
Why is that, man?
The answer will be the same because the universe grows by 1. You have one more number that's no more than 100, which is 100. But 100 is divisible by 5. So it's not a number that's no more than 100 and not divisible by 5 or 7. That is a good question. But 101, we would start to see change. Okay. All right. So next will be, that was sort of our baby example for the inclusion-exclusion principle, but it gets worse. And you might be looking at this and you say, wow, this is pretty bad already. And I do not promise you that this is as bad as it gets. It will get much worse after this. Okay. So what's going on with this? This is just a statement about Venn diagrams with 3 boxes or 3 circles. Okay, maybe this is A, B, and C. And so we have these sort of pairwise intersections right here. So this piece right here, this crescent, is the intersection of A and C. Things that are in A and things that are in C. This section right here is things that are in B and in C. This section right here is things that are in B and in A. So the idea is that what would happen if I subtracted, if I took the size of A plus the size of B plus the size of C, what would be going on in this picture? That would be shading everything in A, shading everything in B, and shading everything in C. The problem would be that I would shade each of these regions twice. This region would get shaded when I shaded A and when I shaded C. This region would get shaded when I shaded A and B, and so on and so forth. So the idea is what I might want to do is I might want to subtract off all of these pairwise intersections. So you would subtract off A intersect B to account for the double count. You would subtract off A intersect C, and you would subtract off B intersect C. Okay. Unfortunately, the problem is that we have three things we've over accounted for our double count. What goes on with this section right here in the middle? I'm going to shade it a little bit. Everybody see my picture? So this core, this thing that's in each of A, B, and C, I shade it one time when I shade A, I shade it twice when I shade B, and I shade it a third time when I shade C. So it gets shaded 3 times, or it gets counted 3 times as we go through this. And then when I subtract off the intersection of A intersect C, I unshade it once, or I uncount it once. When I subtract off the intersection of B and C, I sort of unshade it a second time. And when I subtract off the intersection of A and B, I account for it a third time. So it gets counted 3 times. You'll say counted 3 times. Then I subtract it 3 times. Subtract it 3 times. So at this point, after doing all of these, everything else is accounted for. Everything else has been counted exactly 1 time or shaded exactly once. But this has been shaded 0 times. So I have to go back in and reshade it like this. So this formula is not complete. You have to add in plus the intersection of all of them. A intersect B intersect C. And this sort of gets at what the idea is. It's called the principle of inclusion and exclusion. The idea is we're accounting for things, and as we look at these intersections of stuff, we do it twice. Here, right, we subtracted off the intersection of these 2 things, like twice, multiple times. And so we have to account for that. So we keep doing something and then undoing something else, but we're doing that on smaller and smaller pieces, and so we get a good answer at the very end. Awesome. Any questions on inclusion-exclusion number 2? No, people feel very good. This is the nicest one, I'm sure. All right. All right. Okay. So this problem states, how many, I'll make it big, how many trinary strings of length n are there, including at least 1 0, at least 1 1, and at least 1 2? So a trinary string is like a binary string, except for there's 3, and there's 0, 1, and 2. I don't know if we've discussed those today. So the first question is, we're going to use our subtraction principle again. First question is number of trinary strings. Trinary strings of length n.
So, not to interrupt you, but how would you make an acronym for this principle of inclusion-exclusion sort of thing?
Well, if I were to call it the principle of inclusion-exclusion, that's a great question, which is a nice way to do it, I would call it pi. And then, which is the day of today, as a coincidence. Perhaps you would notice that, perhaps not, but this is thematic for that reason. Okay, so the number of trinary strings of length n, I can think about having n different spots. N spots. The idea of trie is I have 3 things that I can put in each spot. And here normally we say like a binary string is a 0 or a 1, and a trinary string we have a 0, a 1, or a 2. So I have 3 options. I can put a 0, a 1, or a 2 here. I can put a 0, a 1, or a 2 here. 3, so I have 3. And so the total number of trinary strings of length n is 3 to the power of n. 3 multiplied by itself n times. Okay, so this is going to be our universe, and we're subtract off the bad stuff. So what does it mean to be bad in this setting? Well, it's bad if it misses one of the numbers 0, 1, or 2. So bad stuff is strings that miss one of our things. I'm going to have A be strings that don't include 0. I'm going to have B is going to be strings that don't include 1. And C is going to be strings that don't include the number 2. So I've split up my case of bad stuff, which is not including one of these numbers, into these 3 things. And certainly, some strings might exclude 0 and 1, and those are going to be accounted for by my intersections. So A intersect B, this is strings without 0s or 1s. Those will have all 2s in them. A intersect C, this will be strings without 0s or 2s, equals strings without 0s or 2s. Finally, B intersect C will be strings without 1s and strings without 2s. So it'll be B intersect C is given by strings without 1s or 2s. 1s and 2s. What does it mean to be on the 1s and 2s? Is that on keys? To be on the 1s and 2s, does anyone know? If you're like so-and-so's on the 1s and 2s, yeah, maybe it's on the, yeah. Something like that. It's like a thing. I don't know. You hear it like at a show sometimes. Okay, someone's on the 1s and 2s, but it's not B intersect C. Yeah. Okay. Okay, so now we have to do, we figured out what each of these things are, and specifically for this problem, we do have to maybe account for it. So A intersect B intersect C. It's a string taking values from 0, 1, or 2 that doesn't have any 0s, 1s, or 2s in it. Strings without 0s, 1s, or 0s, 1s, or 2s. There are none of those. We'll get to that at the end, though. There are no strings that have 0s, 1s, or 2s if they only take things from 0, 1, and 2. Okay. So we can count first each of these. What is the size of A? I'll do that in the middle here. The size of A is going to be the number of strings of length n that don't include 0s. So all of the entries have to be a 1 or a 2. So we have 2 options for each entry, and so we have n different entries. So there should be 2 to the n. And the same thing with B and C. Strings that don't include 1s, you can either have a 0 or a 2 in it. So there's 2 options for those. You have n entries, so you should have 2 to the n as well. So the size of B will be 2 to the n. And similarly, strings that don't include a 2, all of the entries are 0s and 1s. These are binary strings. So this should be the size of C, binary strings of length n. This is 2 to the n. All right. So now so I've done maybe the hard ones, or I'll claim they're the hard ones, and I leave it to you guys to do the easy ones. How many trinary strings of length n don't have any 0s or 2s? So all of the things I can have are 0s, 1s, and 2s, but I don't have 0s or 2s. So maybe what's the first entry going to be? So if I have a trinary string of length n, and I can't have a 0 or 2 here, it has to be a 1. The next one has to be a 1. The next one has to be a 1, the next one has to be a 1, the next one has to be a 1. So there's only one way to do that, as it turns out. So for these sorts of intersections, A intersect C, for instance, the size of A intersect C, we'll get a little bigger, A intersect C. There's only one way to make a trinary string of all 1s, so that's 1. The size of A intersect B. How many ways can I do a trinary string without 0s or 1s? They have to all be 2s, so this is just 1. Similarly, the size of B intersect C. How many trinary strings do not include 1s or 2s? They're all 0s, so it's just going to be 1. So I have 3 of those, and then putting the pieces together, how many trinary strings, so things using only 0s, 1s, and 2s, are there that don't use any zeros, any ones, or any twos? Zero, yeah, there's no way to do that. Zero, okay. So here we have our total universe, and we're gonna subtract off this total amount, A union B union C, all of the bad things, and we're gonna use the principle of inclusion and exclusion. So I'm gonna erase this piece over here. Right? So the total is our universe minus the bad stuff. All right. Our universe, there's 3 to the n total trinary strings. 3 to the n. And the bad stuff is A intersect B intersects C. And so using inclusion-exclusion, this is going to be size of A plus size of B plus size of C minus size of A intersect C minus size of A intersect B minus size of B intersect C. Oh man, I'm getting, yeah, this one's getting crazy. And then we add back in the size of A intersect B intersect C. We can't forget that, especially in this problem. Okay, so what's going on with this? Now we know what each of these things are, and I'm just going to substitute this in. For a nice short problem, this is going to be 3 to the n minus 2 to the n plus 2 to the n plus 2 to the n minus 1 minus 1 minus 1 plus 0. All right, and I'm going to simplify this a little bit, so this will be 3 to the n minus, I'm subtracting off 3 copies of 2 to the n. So this will be minus 3 times 2 to the n. And then minus times minus is plus, so then I'm adding back on 3 copies of 1. So this will be plus 3 times 1. You can write this if you want as 3 to the n minus 3 times 2 to the n plus 3. Okay. That is a lot of 3s. I think as a curiosity, I think this is interesting. When you look at n equals 1, this formula works. So the idea is, how many trinary strings of length 1 are there with at least 1 0, at least 1 1, and at least 1 2? The answer is none, because you can't have a 0, 1, and a 2 if you only have one position. But when you plug in n equals 1, you get 3 minus 3 times 2, which is negative 3, plus 3 is 0. So I think it's nice when the formula works for us.
6, right?
Pardon?
Negative 6 on that second one?
Yeah, 3 minus negative, well, minus 6 is positive, or negative 3.
You added the I see.
Yeah, I was going fast and loose with it. That's on me, yeah. Cool. All right, questions on this one, this nice little fun problem that we have going on here? No? Cool. Let's look at the next then. All right. Okay, this problem is nice, or in some ways. This is a problem where we don't always do this, but sometimes you do a problem the wrong way because you have to use the principle of inclusion-exclusion. So we'll go through it the wrong way, and then maybe we'll look at what it would look like to do the right way. Okay, so we have access to red, green, and blue paints. We want to figure out how many ways there are to color n balls so that at least one is red, at least one is green, and at least one is blue. Now, I claim the easy way to do this is to first set aside 3 balls, color one of them red, one of them blue, and one of them green, and then color the other ones in whatever way you want. And there's a nice formula for how to do that. This is sort of the easier version of what's called stars and bars, or balls and boxes, and what have you. So we have to use a more complicated version of stars and bars, or balls and boxes, in which you're allowed to take 0 things and then subtract off the bad stuff, because this is in the inclusion-exclusion principle. And it's supposed to be illuminatory. Gosh darn it. Okay. So let's look at this. Where do I have this written down somewhere? Okay. So the first thing is, how big is our universe? How many total? Many total. This is, Ryan, you discussed balls and boxes, right? I don't need to do too much. You discussed stars and bars?
I didn't.
Okay, well, we're gonna do stars and bars. All right, here we go. Let's look at, yeah, how many total? So I'm gonna count this in an interesting way. So I'm going to think about arranging some stuff, as we often do in combinatorics. And the things I'm going to arrange are my balls that are sort of indistinguishable, and also the divisions between colors. So I'm going to think about having okay, n balls, and then I'm going to have 2 dividing lines. And what happens with these dividing lines is I'm going to take an arrangement of my n balls and my 2 dividing lines in some fashion, and I'm going to translate that into a question about how do I paint some balls. So I'm going to look at this right here. I'm going to look at an example with having n equals 5. I'm going to think about this right here. Okay, so the circles, or the dots, are going to be my balls. And the dividing lines are these bars right here. And so the idea is, everything to the left of the first dividing line, I'm going to maybe color red. Everything between the 2 lines, I'm going to color blue. And everything to the right of all the lines, I'm going to color green. All right. Now, and this is, no matter how I arrange this, I'm always going to use this approach. I'm always going to do everything to the left of the lines red, everything between the lines will be blue, and everything to the right of the lines will be green. Now, one thing that I will notice is what happens if you have 2 lines next to each other. For instance, if I had this arrangement right here, this would mean I would have 3 red balls. I have 3 dots to the left. I have 0 blue balls because there's no dots between the 2 dividing lines, so 0 blue. And I have 2 dots to the right, so I have 2 green. Okay. So my statement is that I should be able to extract for each way I can arrange n balls and 2 dividing lines. I count some coloring of my balls using these 3 colors. And this also shows what happens when I have bad stuff happening, right? When I have 0 of one color. Okay. So with that, what is how many total to answer my question? So to answer the answer here, how many total? Well, I can think about just having, I have n plus 2 total things, n balls and 2 dividing lines, and I'm picking 2 positions for them to have dividing lines. So I have n plus 2 positions, and I'm picking 2 of them to be my vertical lines. So it's n plus 2, choose 2 is my total. Okay. So now let's think about, this is my universe, and I have to think about subtracting off the bad stuff. So for my bad stuff now, I'm going to have A is going to be ways to paint the balls without using red. And then I'm similarly going to say, in some more shorthand, B is going to be the ways to paint the balls using no blue. So it'll be this with no blue. And third, C will be the ways to paint the balls using no green. All right. So the intersections, right? A intersect B, This is ways to paint the balls using no red or blue, for instance. Red or blue. A intersects C. This is no red or green. And then B intersects C is going to be no blue or green. All right. And again, if you want to look at maybe the nicest one, A intersect B intersects C. This is all the ways to paint the balls using red, blue, or green, using no blue, no red, and no green. Okay. So we figured out what all these things have to be. Now we have to figure out the sizes of them. So we'll figure out the bad stuff. We'll use inclusion-exclusion. We'll go from there. First question, if anyone knows, what is the size of A intersect B intersect C? Anyone got this? Anyone feel good about that? All right. How many ways are there to paint balls using red, blue, and green that don't use any red, any blue, or any green? 0. Yeah, there's no ways to do this. That's good. We're getting these ones out of the way first. What about, for instance, if I don't use red or blue, I have to use green for all of the balls. There's only one way to do that. So maybe we see the size of A intersect B equals 1. And you can similarly think, how many ways can I paint these balls using no red or no green? Well, then everything has to be blue. There's only one way to do that. And you get A, we do comma, A intersect C equals 1. And then if I don't want to use blue or green, I have to use red for the rest of them. So there's only one way to do that. So the size of B intersect C, which is the number of ways to paint these balls without using blue or green, is just 1. Okay. We're getting closer. Now we have to figure out the size of A, B, or C. I claim by symmetry, these are all going to be the same thing. The number of ways to paint it without red will be a lot like the number of ways to paint without blue. You could just, instead of everything that was blue, you change to red. So they connect. So first we'll just see what is the number of ways to paint balls without using red. So all my colors come from red, blue, and green, and I'm not using red. So this is just asking how many ways can I paint n balls using blue or green. All right. This is a problem much like this. We have to use this sort of idea again. We can think about having, instead of having n balls and 2 dividing lines, we can have n balls and 1 dividing line. And so we're trying to think about where we put this dividing line. Everything to the left of it will be blue, and everything to the right will be green. So we use this same sort of idea that we had before. This ends up being n plus 1 choose 1 ways to do that, which is n plus 1. Okay, and we can think about this right here. The idea is, okay, we have n balls. Some of them are going to be blue and some of them are going to be green. So just pick a number. How many of them are going to be blue? If you pick 0, 1, 2, 3, up to n, the other ones have to be green. So this gives you the same count right here. The same idea is true for the size of B, will also be n plus 1, and the size of C is n plus 1. Okay, so again with the space limitations, we're going to move over here. So our total is going to be universe minus the bad stuff. Okay, the size of our universe is n plus 2, choose 2. And the size of the bad stuff is given by inclusion-exclusion principle, our fun formula. So I'm going to erase this right here after copying up there. This is going to be minus the size of all the bad stuff, which is, in parentheses, size of A plus the size of B plus the size of C minus the size of the intersection of A and B minus the size of the intersection of A and C minus the size of the intersection of B and C plus the intersection of all three. A intersect B, intersect C. All right. Now we can just take all of the numbers that we know and translate them into this problem, and we're almost home free. So this is n plus 2, choose 2, minus, what is this going to be? This will be, size of A is n plus 1, plus 1, plus n plus 1, plus n plus 1, minus, the size of these intersections are all 1, these first three, minus 1, minus 1, minus 1, plus intersection of all three is just 0. Okay? So simplifying here, we have 3 copies of n, we have 3 copies of positive 1, and we have 3 copies of negative 1. So I'm going to combine those. We have, this is equal to n plus 2, choose 2, minus 3 copies of n. This is 3n plus 3 copies of 1, so that's plus 3. 3 copies of negative 1 turns into a minus 3. And I can simplify this as this is equal to n plus 2, choose 2, minus 3n. Cool, all right. I think that feels pretty good. This is our final answer, and this is some number for n. All right, pause. Questions on this idea? This is a nice, this idea with the balls and the lines is like a very famous notion in combinatorics, in discrete math. I certainly didn't make it up. But I might be the most recent person to do it, you never know. All right. So how many people here have made, or online too, people on the internet, have made a password before? Yeah, a lot of people out there. That's good to hear. I too have made a password before. And as time goes on, more and more times you make a password, they say, hey, you have to make at least one of these 3 characters. You have to have an uppercase letter, you have to have a number, maybe a symbol of some sort. So here we can ask the question, how many ways can you do that? Like maybe you might want to figure out, is it easy to check all of those? You would want to run through all of them. So the question here, we have how many 8-character passwords from the standard set of 95 characters use at least 1 capital letter, 1 symbol, and 1 lowercase letter. All right, we're going to do the same thing we've done with the last couple times. We're going to figure out the total, and we're going to subtract off the bad stuff. We're going to use inclusion-exclusion on the bad stuff. So what is, first we have to figure out what is like our universe. So question first, how many 8-digit passwords are there using these 95 characters? Digit passwords. Okay, so I have, 8 character passwords? Yeah, 8 character passwords. Okay, so I have 8 spots. 1, 2, 3, 4, 5, 6, 7, 8. 8 spots. I can put any character in the first spot, so I have 95 options. Any in the second spot, so I have 95 options. I have 95 options for all of these. They're all going to be 95. Using the product principle, we multiply all these together. So there's 95 to the power of 8 total options. Total password options. Okay, so now we have to figure out the bad stuff. We have to figure out how many passwords now maybe don't use a capital letter, don't use a lowercase letter, or don't use a symbol. So we have A, B, passwords without a capital letter. B is going to be passwords without a lowercase letter. Case letter. And then C will be our passwords without a symbol. Without a symbol. Symbol. And this is, thank you. Okay, yeah. At first, when I came up here, because it had come up a couple times before, I thought I would do something in the spirit of this, where I was like, every time I was writing when the screen was big, I was going to do 1 push-up the first time, and 2 push-ups the next time, and 3 push-ups the third. But if people maybe see, that number can grow quite quickly. And I felt like, based off of my performance in the first hour, I decided I wasn't going to do that. But maybe from now on, yeah, if it comes up. Maybe people in the audience, maybe people at home, you can do a push-up every time I'm talking like that. You can get huge in 3 more hours. Okay. So I want to highlight that this sort of situation, we've done this for the last few problems. This isn't the first time, right? We have our bad stuff, and we think about, okay, well, we have to use a capital letter. So one of our bad things will be don't use a capital letter. We have to use a lowercase letter, so we're going to split part of our bad stuff is into passwords that don't use a lowercase. And our third bad thing is not using a symbol. So our third part of our bad stuff is not using a symbol. And then we use inclusion-exclusion on these. So I won't write these down, but we can similarly think that the A intersect B is just going to be passwords without a capital letter or a lowercase letter. And we'll get to that in a second. So first, what's the size of A? So passwords without a capital letter, there's 26 capital letters. So let's think what this is. So we have 8 spots. 1, 2, 3, 4, 5, 6, 7, 8. And I can pick anything here from my 95 that's not a capital letter. So I have 95 minus 26 options. That ends up being 79? No, 69. 69 options. 69 plus 25 is, or 26 is 95. 69 options. I have 69 options here, 69 options here, 69. All of these are going to be 69s. So the total number of passwords that don't use a capital letter is 69 to the power of 8. Okay, I'm going to erase this calculation because we're going to want the space. All right. What's the size of B now? Passwords without lowercase letters, so there's 26 options for symbols for that as well. So I have 95 minus 26 options for the first thing, 95 minus 26 for the second. You again have 95 minus 26 to the power of 8, which is 69 to the power of 8. Finally, passwords without a symbol, this sort of came up earlier. There ends up being 26 capital letters, 26 lowercase letters, so that's 52 letters, and there are 10 digits from 0 to 10. So it's 62 total characters are not a symbol. So you have 33 symbols, 62 things that aren't a symbol. So the size of C, I have 62 options for my first. No, sorry, I have, 66 options for my, 62. 62 options for my first, 62 for my second, 62 for my third, etc. You end up with 62 to the power of 8. 33 symbols, 33 plus 62 is 95. Okay, whew. I'm off the rails a bit, okay. Yeah, okay, 33, yeah. 26 plus 26 is 52, plus 10 is 62. So this is alphanumeric passwords right here. Okay, now we can think about the size of A intersect B. So what does that mean? That's a password that doesn't use a capital letter and it doesn't use a lowercase letter. So we lose all those possibilities. So for the first thing, we have to use a symbol or a digit, and we have to use that for each of those. So this should be 95 minus 26 minus 26. 26 to the power of 8, because we can make that selection 8 times. And this ends up being 43. 43 to the power of 8. I think the most fun thing of this thus far has been seeing people's ability to do this sort of math deteriorate. And I get to witness it firsthand now. Okay. So what about A intersect C now? So this is passwords that don't use a capital letter. There are 26 of those. And then passwords that also don't use a symbol. There are 33 of those. So how many options do I have for each entry? So it's 95 minus 26 minus 33, which is 36 to the power of 8. So this is 36 to the power of 8, which is a big number too. Finally, the size of B intersect the size of C. So I have, again, I can't use a lowercase letter, I can't use a symbol. 26 of these, 33 of these. I have 95 minus 26 minus 33 options for each entry again. So you have 95 minus 26 minus 33 to to the 8, which is 36 to the 8. Now, every other time we've done this that I write down A intersect B intersect C, and we say it's 0, but we don't always get to do that. This time we have something non-trivial. So A intersect B intersect C. This is things that don't use letters, don't use symbols. All that's left is the digits 0 through 9. So you have 10 options for each, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So you have 10 options for each of your 8 entries. Okay. So using the subtraction principle now, we do our total things in the universe, and we subtract off the bad stuff. So total equals universe minus bad stuff, which is going to be 95 to the power of 8 minus size of A plus size of B plus size of C minus size of A intersect C minus size of A intersect B minus size of B intersect C plus the size of A intersect B intersect C. Close parenthetical. All right. So now what we got to do, as we've done the last few times, we've tabulated all these values, and we just got to plug them in the right arrangement. Okay, so what's this going to be? So these things I'm adding, these 3 I'm subtracting, this one I'm adding is sort of the pattern going on. So this is going to be 95 to the power of 8 minus, what is this? 69 to the 8 plus 69 to the 8 plus 62 to the 8 minus 43 to the 8 minus 36 to the 8 to the 8 minus a second copy of 36 to the 8. That's for this one down here. Finally, plus 10 to the 8. A paltry number compared to the rest. All right. Close it like that. And if we want to, we can put this all in one line. We have 2 copies of 69 to the 8. We have 2 copies of 36 to the 8. It'll all fit nicely. We write this as 95 to the power of 8 minus 2 times 69 to the 8 minus 62 to the 8 plus 43 to the 8 plus 2 times 36 to the power of 8 minus 10 to the 8. You might notice, again, we've seen a lot of signs switch because we were subtracting them. So instead of adding 69 to the 8, we've subtracted it off. Sign changes. This is our final answer. Does anyone know what that number is? No, big number. Yeah, it could be. Actually, it's probably pretty big.
We saw 95 to the 8 a couple of times already.
Yeah, that's a pretty big number. And these are smaller numbers. I think it's definitely still positive. Yeah, I mean, I definitely have made a password with a capital letter, a lowercase letter, and a symbol in it of 8 digits. So I think it's at least 1. Cool. All right. Cool. We did see earlier, and this is good advice, that in general, the best thing you can do is use more characters than to use like a longer password of all lowercase letters is usually better than one of these things, and they're easier to remember, maybe. All right. Go to the next one here. Make it big while I erase. Okay. All right. The problem is, how many integers between 1 and 1,000 are divisible by 3, 5, or 7? So before we looked at how many integers between 1 and 1,000 are divisible by, between 1 and 100 are divisible by 5 or 7. And so we could tabulate it like this. So the first thing that we observed is that the number of integers less than or equal to n, and this is positive integers, but positive integers, we'll say. Positive integers divisible by k is the biggest number, that's biggest positive integer that's less than n divided by k. So we've seen this a few times before. We worked through this problem. That's another push-up. Another 2 push-ups. Okay. I'll do them tomorrow. I'll do them in class. Okay. I don't think I wouldn't have enough time to get to the content if I was just pressing away. Okay. So this is true. This is the number of positive integers less than or equal to n divisible by k is this floor right here. All right. So we saw this before. We had 99 over 5, for instance, and we got 19 out. Okay. So we're going to use our same idea, our subtraction principle. The first question is, well, isolate this. My first question, how many positive integers are there? Pos ints less than or equal to 1,000. I know we've had some fresh blood in here for the last couple of problems, so I'd like to hear an answer from the crowd and someone out there. How many positive integers are there less than or equal to 1,000? 1,000, yes. Less than 1,000 would be 999, but we also are allowed equal to, which is nice in this problem. So it ends up being A is 1,000. So again, we have our universe is going to be this total right here, which is 1,000, and we're going to subtract off the bad stuff. And the thing is, bad stuff means being divisible by 3, by divisible by 5, or divisible by 7 in this case. And so we're going to set our A, our B, and our C to be our corresponding sets. So A is numbers that are positive integers less than or equal to 1,000 and also divisible by 3. B is going to be divisible by 5, and then C is going to be divisible by 7. Okay? And so for this one, I will make a note of this. What does it mean to be in the intersection of A and B? This means you're divisible by 3 and divisible by 5. And because these are prime numbers, we know what that means. You have to be divisible by 15, which is 3 times 5. This is divisible by 3 times 5. A intersect C is divisible by 3 times 7. B intersect C means you're divisible by 5 times 7, 35. And then finally, A intersect B intersect C. This means you're in each of these 3 categories. You're divisible by 3, you're divisible by 5, and you're divisible by 7, which means, because they're all prime, you're divisible by their product. This is divisible by 3 times 5 times 7. Okay, and then specifically we mean for each of these, we actually mean this, and they all have to be less than or equal to 1,000. So using this idea, the positive integers less than or equal to 1,000 divisible by, for instance, 3 will be the floor of 1,000 over 3. So we can take this idea and then translate that for each of these. For instance, the size of A is going to be the number of positive integers less than or equal to 1,000 divisible by 3. This should be equal to the floor of 1,000 over 3. It's the biggest number you can multiply 3 by and be less than 1,000. This is 333. Right? I'm going to do a lot of mental math on this one, so someone please correct me if I'm wrong. Size of B is going to be the floor of 1,000 over 5, which is 200. The size of C is going to be the floor of 1,000 over 7, which is 144. Someone maybe check that for me. Okay. The size of, now we'll do the size of A intersect B. This is the floor of 1,000 over, right? A intersect B is number divisible by 15. So it's 1,000 over 15, which is, anyone know?
The 144 is a 142.
142? Yeah, that sounds about right. Okay, I'll let you guys calculate these as I go, and then I'll come back to it as you can shout it out to me. The size of B intersect C is 1,000 over 35 equals something. The size of A intersect B, B intersect C, we need A intersect C. This is going to be the floor of 1,000 over A intersect C is divisible by 3 times 7, so that's over 21, which is something. And then we'll do the size of A intersect B intersect C equals the floor of 1,000. 3 times 5 times 7 is 105. 105. I know this one is going to be less than 10.
That one's 9.
This one's 9. Yes. Does anyone know what these ones are? Anyone here? Any brave souls?
47 is the one you're pointing. Nope. That one's 47.
47, yeah, because 20 times 50 is 1,000. That sounds about right.
15 is 66.
66 right here? Okay. 66. And then on this one over here, I'm going to guess that it's like 29, 28? 28. Nicely done. All right. You know, it takes a village, they say.
Rounds up to 29.
It does round up to 29. That is correctly observed. Okay, so again, we're going to use our universe minus bad stuff approach. So the total equals universe minus bad stuff, which is 1,000 minus. All right, let's get this. Let's get this. Okay, 333 plus 200 plus 142 minus 66 minus 28 minus 47 plus 9 plus 9. And this is a number. Yes, I see a hand.
We're looking for the ones that are divisible by 3, 5, or 7.
Oh.
What's the set of stuff that's not divisible?
That is a great question, Joey. Yeah, you are so right. We don't have to use the subtraction principle on this. I misread this. I set myself up for a bad time. Okay, so we can just look at this right here. So we just need the set of things that are divisible by 3, 5, or 7, which was calculated by this. So our bad stuff is now our good stuff. I guess that's what they call a twist. Well, with that, then, so I'll move this 3 back. This is way easier to calculate now, and we'll just do it. Okay, so 333 plus 200 plus 142, this is 533, 675. 675 minus, what is this? This is 94, 141. 41 plus 9. This is equal to 534 minus 9, which equals 520. Plus 9, plus 9. This is equal to 543. Thank you. It's easy to get tripped up on these ones. We got there, all right. 543 integers are divisible by 3, 5, or 7. So this is a lot of them. This is more than half, which seems like a lot, but then you think of, these are 3 of the pretty small primes. But 500 of the numbers between 1 and 100 are divisible by 2. So somehow 2 is still like the dopest prime. Some of these are also divisible by 2. We won't look at that here though. Cool, all right. Going to the next one. More primes. We have been looking at primes for a long time now, so I think it's a good time to define them for anyone who doesn't know in the audience. So what is a prime number? A prime number is a number that's only divisible by itself in 1 in terms of by integers. So if you want to write it as a product of two integers, two positive integers, it has to be itself times 1. Okay. We might not actually solve this problem, but we'll talk about what's sort of going on with it. No, I was just going to skip it. There ends up being 4 things, and I don't want to set up how we're not ready for it, maybe. But we'll talk about what's going on later. Okay, so my first claim, if a number between 1 and 100 is not prime, it is divisible by 2, 3, 5, or 7. Which I think is not obvious. This really wasn't obvious to me. Okay. Does anyone know what's special about these primes? Why I might write these primes up right here? They're pretty small. These are some of the smallest primes there are. And notice that each of these primes, I'm going to say, each of these is less than 10. Each of these is less than 10. Okay. So what I want to do is then so take some number that's not prime. Take we call it a composite number. Composite number. Maybe that's call it K. And I want to write it as smallest prime factor. Smallest prime factor times the rest. The rest. So this is P, I'm going to call this Q. So for instance, if I had the number K equals 50, I would write this as its smallest prime factor, which is 2 times 25. All right? And so the thing that I want to notice is that what has to happen is that P has to be less than or equal to Q. Okay? The idea is that if Q is smaller than P, then it might have if it's a prime, then we have a contradiction. And if it's a composite number, it can be split into things that are also smaller than P. And so we have a contradiction. So really what it is maybe we mean P is less than or equal to Q because it might be a prime power. I know you were mad at me for this. Okay, so P is less than or equal to Q. What this means is going back up here, that means that P times Q is greater than or equal to P times P. And what I've done here is I've replaced this Q with another P. And so if you multiply something smaller, you get a smaller value. So this has to be greater than or equal to P times P. And so the idea is if a number is no more than 100, and it has no divisor less than 10, I'll write this down. Okay. Take a composite number whose smallest prime divisor is bigger than 10. And we'll call this number K. Smallest prime divisor, that's this number P. So that means that K equals P times Q for some, the rest of it Q, has to be bigger than or equal to P times P. And specifically, if it's bigger than P, that means its smallest prime divisor is bigger than 10. That means P is bigger than 10. So that means that this is bigger than 10 times 10. 10 times 10 is 100. Okay, So if you have a composite number whose smallest prime divisor is bigger than 10, that means that number is bigger than 100. So if you have some composite number that's smaller than 100 or equal to 100, it has to have some prime divisor that's less than p. So this notion is reversing this sort of string of logic, where it's called using the contrapositive here, which maybe you've heard of and maybe will be in a future math marathon. Okay, so we have this notion. I'll go big here. Yep, classic. That's 3 push-ups. All right, so we have this idea right here. So we know that we have to figure out, we have to count the number of positive integer or prime numbers between 1 and 100. Those are all the numbers that are not divisible by 2, 3, 5, or 7, plus the numbers 2, 3, 5, and 7. So if we wanted to set up our, like as we've been doing this before, we can have our universe minus bad stuff. And so bad stuff is things divisible by 2, 3, 5, or 7. But that's 4 different things. And normally we only know how to handle this if we have up to 3 different bad stuffs. So we need a more involved setting for this. So again, we could have A is numbers divisible by 2, B is numbers divisible by 3, C is numbers divisible by 5, and maybe you could have a D as things divisible by 7. But we need more involved machinery to handle that problem. Okay, wait, all right, there we go. So to do so, we have this, I guess, behemoth. So this is, I think, is the first inclusion-exclusion was a little spooky, the second one was nice, and this one has a lot going on. So we won't go over into too much detail what this sort of means. I actually won't even use this problem as stated. What this is getting at, though, is before we had this situation, this notation is quite involved, is we added up all of our items, A, B, and C, and then we subtracted off the intersections of 2 of them, and then we added on the intersections of 3 of them. What you do next is you subtract off the intersections of any 4 of them, add on the intersection of any 5, subtract off the intersection of 6, etc. So you have that alternating thing going on. I'll make myself small. What's going on right here? You'll notice that, where's my hand go? Okay, yeah. Just here at the bottom, this -1 to the size thing is accounting for that alternating add and subtract. As you take increasing powers of -1, you have plus and minus, and then you have times the size of the intersection. So we're doing all we've been doing, adding the size of all the things, subtracting off the size of the pairwise intersections, adding on the size of the 3-way, subtracting the 4-way, etc. All this notation does is encode that with symbols. You don't really have to know the symbols too much. I will write down, though, another formulation of the inclusion-exclusion principle as we're going to use it more often in these next couple problems. Okay, so I'm going to press this button here. Okay. So I'm going to write it as follows. Given a universe U of items and subsets A1, A2, up to AN of the items, the number n sub empty set of items belonging to none of the subsets of the subsets is given by n sub the empty set is going to be written as this sort of summation. Here we look at all index sets. This is much more involved than we need to know. Times -1 to the size of s times the intersection A sub I. Okay, so again, this is still a lot. This isn't any better than the notation we had before, I don't think. But what does this tell us? This sort of rephrases the problem. This says, hey, if I have bad stuff, what is the set of things that aren't in the bad stuff, is how this is phrased. The A sub i's we can think about as being the bad stuff. We've sort of rephrased this in our subtraction principle mindset. So we have the number n naught is the things that belong to none of those subsets, so it's not in the bad stuff thing. and this gives us this idea. All that's going on right here, this is telling us whether or not we add or subtract things. And this is just saying intersections of bigger and bigger sizes. So if the intersection of one thing, we're adding all of those, two things, we're subtracting, etc. Cool. All right. This is equivalent to the formulation we have here in the slides as well, or it can be viewed equivalently. They're sort of the same thing, they're just presented differently. But this will help us for the next couple problems that we look at. This will be of that sort of flavor. Okay. So I'm sure people feel good. I'd ask for questions. I can't see the chat. Maybe I can alt-tab. I don't want to break anything. So I'm not going to go to the chat. I'm not going to break. But if people have comments, then you can let me know. If you have questions about inclusion, exclusion, you can do that too. Okay. All right. People, it is a little bit of kind of a crazy one, but we're not going to work with it too much. We're going to, again, for here, if you'll notice, like in this problem, we have sort of just a formula, and we're just going to show that we can translate this formula from the one that we had before. Okay. So we're going to say that A and B are finite sets. So again, they're just sets, and the size of A is n, the size of B is k, maybe. We say that a function f is onto or subjective if the image of f includes all of B. This is sort of a little more technical than we need it to be. But the idea is that we're thinking about if you have a set A over here and a set B over here of different sizes, a function can be viewed as it just takes for everything in A, it draws an arrow to something in B. Everything in A has exactly one arrow coming out of it to one thing in B. We can think of functions in this way between finite sets. So what does it mean in this setting for a function to be surjective or onto? It just means that if you look at B, every single dot has an arrow pointing to it. That's all we mean for something to be surjective. Every single dot over here has an arrow pointing to it. This is everything that's going on with that. Okay. So this is the idea of what onto is. So with that, and actually maybe we'll keep that. I'll redraw the picture if we have. Okay, we have maybe something like this. Okay. Okay. So the total number of functions can be counted. The total number of functions is if I have n things over here, each one gets one line drawn to something over here. So the total number of functions is like, total is n to the power of k. We have, sorry, it actually should be k to the n. K to the n. I have k options for this first thing to map to, k options for the second thing to map to, and I have n things. So this is like a binary, or this is like a string with a universe of size k, or an alphabet of k. Okay. So what would it mean for something to be bad here? What is bad stuff going on? That's what our A1, A2, A3, sort of these subsets are going to represent. Bad stuff means that I have an element over B that doesn't have an arrow pointing to it, right? There's a thing in B that isn't in the image of F, doesn't have an arrow going to it. So bad stuff is going to relate to things in B without an arrow pointing to them. Without an arrow pointing to them. All right? Okay. So what I'm going to do, I'm not going to have actually n different things. I'm going to have, I'm going to label the things in B, 1, 2, 3, all the way up to I have k total things. So I'm going to label them with just 1 up to k. And I'm going to have A sub I be the set of functions that don't have an arrow to element I, that don't include I in their image. Okay? So that means a sub 1 is the set of ways to draw arrows from over here to over there that doesn't put any arrows to element 1. A sub 2 is all the ways to draw arrows from things over here, over there, that don't send any arrows to the number 2, etc. So my first question is, there's a symmetry to this. Does anyone know what the size of a sub, for instance, a sub I for any of these i's? Well, normally I have k options over here to send something to. But this, I'm saying here, I want to look at a function that doesn't map anything to I. So I only have k minus 1 options. So here now, my alphabet is k minus 1, but I still have n things. Okay. Next, you can look at, like, sort of, you might consider what's going on with a sub I intersect a sub j. So maybe you care about, for instance, I equals 1 and j equals 2. We're thinking about all the functions that don't send arrows out to a specific pair of elements. So maybe if that's 1 and 2, all of the ways to send arrows out to things between 3 and k. That means I can't send an arrow to I or j. So my universe, my things I can select for targets of my function, this is going to be k minus 2 to the size of n. All right? And so in general, if we have some sort of, the idea is we have some sort of set of indices, like if we have like some set S is contained in 1, 2, 3, up to k. This is some set of things over here. We could think about the functions that don't map to that set if we want to miss like 1, 2, 7, 12, and k, for instance. We can think about, we can represent the intersection of these functions that don't map to these elements in this way. So this is a sub, we'll write this as intersection of things in that index set, I in S of a sub I. That's how we represent this. This is just saying things that don't map to any of those is given by n minus the size of S, sorry, k minus the size of S.
Screen size.
To the end. Thank you. That's 4. Okay, cool. All right, k minus the size of S to the end. I'll write this as a better k. All right. Okay, so there's a couple things I want to notice right here. We're setting up inclusion-exclusion correctly. So this is sort of extracting these sorts of ideas, and we know what these intersections mean. Now, I'll say that if you look at all the functions that don't map anything to point 1, some of them don't map things to point 2 either. So we're sort of over-counting those when we look at the size of a sub 2. So we need to use our inclusion-exclusion idea, which looks at like an alternating addition and subtraction. Okay? But the idea is, like with this, the number of things that n naught, the things that aren't any of the bad stuff, is the things that don't miss any points. So n naught in this setting here, n naught is a number of items belonging to none of the subsets, is things that don't miss any points. So those are things that if you don't miss any points, you are on to. It's another sort of idea. So what does this mean? This means that n, or maybe n sub null, however you want to phrase this, it should be given by the size of, so for any index set in the numbers, sorry, this should be 1 up to k. Here, n, we have k things, not n things. So this is the set here, 1 through k. All right, should be negative 1 to the power of the size of the set S times the size of that intersection right here, which is just k minus S, size of S to the power of n. Okay? And we're not quite in the form we want yet though, right? This here is a sum that's looking at all possible subsets. But in the problem right here, we have a sum that just ranges from j equals 0 up to n. And it has a binomial coefficient going on in there. And so what happens here, we could sort of think about this in the next method, or get a little more space. Okay. My question is, how many ways can I select a set of, I think there's a typo in this problem, oh well. This should be, I think this should be, the size of A is K and the size of B is N. We'll work it, we'll fix it in post. The idea is in the formula the K's and the N's will be backwards. So select a set of size J from B. Okay? So B is a set of size K, and I want to select a set of size J. I can do that in one of K choose J ways. Okay? And the idea is for any of those sets here, right, all we care about for a set, the number of ways to have a function that misses those, is just cares about the size of it. Each of those corresponds to K minus the size of J, which is, or size of S, which is just J, to the power of N functions. Using this idea, this is something pretty sophisticated, so if you missed this, that's all right. You learn this, I think, as time goes on. Instead of indexing over all sets, and looking at this right here, I'm going to index over the size of sets. And I say, hey, all I care about is the size of each of these sets. So I'm going to ask myself, how many sets of each size are there, and how big is the contribution for each of these? So instead of indexing over sets, I'm going to index over size of sets. This should say that n naught, or n sub null, should be equal to the sum from j equals 0. And here I'm going to have k, again, because I have, there's a mix-up in the slides. N and k are reversed in the statement from how they'll be in the problem, but that's the only thing that'll change. So we'll have n sub null should be the sum from j equals 0 to k of k sub j, the number of ways to pick an n set, or sorry, a j set from B, times the number of corresponding functions, times k minus j to the n. And we again have to have our inclusion-exclusion. Each of these has this size variance, so that'll be times -1 to the size of the set, but the size of the set is just lowercase j. So if I'm not mistaken, other than the fact that the k's and the n's are in reverse order, which sort of sucks, we're good to go right here. Cool, all right. Questions on this one? This one's sort of nice. Functions are things people care about. Surjective functions are one of the two things people care about most. Maybe injective, or and then the combination is bijective. So knowing how many ways you can do that is a thing we might be interested in. Cool. All right. All right. We'll go big picture. I'm going to take a sip. We're closing in on the end of inclusion-exclusion. This is where it gets really deranged for anyone who's stuck around.
Wasn't arranged already?
Oh no. Okay. So I present to you the hat check problem. This is, or maybe a slight rephrasing of the hat check problem, which is stated as follows. A theater is attended by n hatted patrons. They each leave a hat at the hat check. And so maybe I think the idea is you hear that the power goes out and they all leave and then it's in the dark and then so they can't see whose hat is whose. So the question is, how many ways can the hat check hand one hat to each of the n patrons such that no one gets the correct hat back? So there's a lot of ways to hand these hats back to patrons. I think there's n factorial if you think about this. You can think about labeling the people 1 through n and their hats 1 through n. And you think about all the ways to give their hats back. It's going to be a permutation of the numbers 1 through n. Okay. So we'll do this at first. We're going to solve this problem smaller first. And we're going to introduce the notion of a derangement. A derangement is a permutation where object I is not put in position I. So for example, 3, 2, 1, 5, 4 is not a derangement as 2 is in the second position, nor is 5, 4, 3, 2, 1 because 3 is in the third position. So on the other hand, 2, 1, 5, 3, 4 and 5, 4, 2, 1, 3 are derangements. So the idea is you can think about writing, like if you have, right, 1, 2, 3, 4, 5, and then so that's just integers 1 through 5. A permutation, we write 3, 2, 1, 5, 4. It's not a derangement because we have the same number on top and bottom. So this is not a derangement because we have this happen. Not a derangement. Right? But if you never have the same number on the top and the bottom as you write your permutation in this fashion, you have a derangement. Okay. So we'll do 2 small problems. We'll count the derangements of 1, 2, 3 and 1, 2, 3, 4 using inclusion-exclusion. Okay. So what's the issue with a thing happening in a derangement? It's a fact, or it's a permutation where one number is fixed. For instance, instead of, as we saw before, you can think about 1, 2, 3, 4, 5, and a permutation just rearranges these. So if you have 5, 2, 4, 1, 3, we can think about just shuffling these things around. This is not a derangement because 2 is fixed. 2 is fixed. So it's not a derangement. Not a derangement. Okay. So we're going to think about our bad stuff, our set of bad events are going to be fixing elements from 1 up to 5, or in this case, 1 up to 3. All right. All right. So let's count the derangements. The total number of things, total, it's going to be number of permutations, or maybe this is our universe. Universe is the number of permutations of numbers 1, 2, 3. Of 1, 2, 3. There's 3 elements in this set, so it should be equal to 3 factorial. Okay? Our bad stuff is fixing one of these 3 things. So A sub 1 is permutations that fix 1. A sub 2 equals permutations that fix number 2. And A sub 3 should be the permutations that fix 3. Okay, I'm first going to count each of these, and then we can look at the number of ways that fix a pair of them and all 3. Okay, so how many ways can we have a permutation that fixes number 1? So that looks like we have 3 things here. The first thing has to be a 1 because 1 is fixed. Then I have 2 options. I can pick either 3 or 2 for the next one. So it's 1 times 2, and then after I've picked 2 of them, the third one's decided. So it's like this. So there's 2 of those. For A sub 2, the number of permutations that fix 2, well, I have to put a 2 here, so I can pick what goes in this middle spot in one way. I can pick a 3 or a 1 to go here, so I can do that in 2 ways. And then this third one is decided. It's the third one I haven't picked yet. So this is 2. And then similarly, you can think about the number of ways that fix 3. It's the permutations 1, 2, 3, and 2, 1, 3. So this is also just going to be 2. Okay. So now we can think about what are the permutations that fix A, that fix 1, and fix 2. Maybe I'll label it specifically size of A1, size of A2, and size of A3 to be abundantly clear. So the size of A1 intersect A2. We have to think about permutations that fix the first entry, fix the second entry, and the third can be whatever we want. Okay, so we have 3 things. This has to be a 1, so we put a 1 there. There's one way to do that. This has to be a 2, so we put a 2 there. There's one way to do that. And the third one, I mean, it could be anything, but we only have one thing left to place, so there's only one way to do this. This is 1. And similarly, you can find, if you fix two of them, the third one is decided. So we also have to have A1 intersect A3 equals 1, and A2 intersect A3 equals 1. Finally, how many ways are there to have a permutation that fixes all of the elements? One, you just fix all the elements. So we also have A1 intersect A2 intersect A3, size of equals 1. This is accounting for sort of just fixing everything. It's just the permutation 1, 2, 3. Okay, so putting this all together, we have total equals universe minus bad stuff, which is equal to 3 factorial minus bad stuff is 2 plus 2 plus 2 minus 1 minus 1 minus 1 plus 1. Right? This is a sub 1, a sub 2, a sub 3, size of the pairwise intersections, size of the three-way intersections. All right? So we have 6 minus 2 minus 2 minus 2 plus 1 plus 1 plus 1 minus 1. Okay, this is 6, 4, 2, 0, 1, 2, 3, 2. Okay. There are 2 permutations that are derangements of 1, 2, 3. Okay. And so what are they? We could probably figure out what it's going to be. So what would a derangement look like? It can't fix anything. So so the idea here, maybe I'll write it in a slightly different way, in the way we had before. So I have the numbers 1, 2, or 3, and I have to write each of these below it such that way I don't have the same number above or below. So this one right here, it can't be a 1, it has to be a 2 or a 3. Let's suppose it's a 3. Well, what goes here? It can't be a 2. I've already used 3, it has to be a 1. This one has to be 2. Similarly, if you have 1, 2, 3, suppose the first thing is a 2. I'm going to say, I can't put a 1 here, because then I'd be forced to put a 3 in the third place. So I'm forced then, instead, to put a 3 here, you get a 1. So these are my 3 derangements, 3 ways to give these hats back to these 3 patrons in this fashion. Okay. Let's count the derangements of 1, 2, 3, 4 as well. You can settle in for this. So here, our universe is going to be the number of permutations of 1, 2, 3, 4. All right, and so that's going to be, the size is 4 factorial. As we saw, a number of ways to arrange a 4-element set, it's 4 factorial. Okay, what are the things what's my bad stuff? Bad stuff is fixing any of these 4 elements. So we'll have a sub 1 equals permutations. I'll say fixing 1. A sub 2 equals permutations. Fixing 2. A sub 3 is permutations. Fixing 3. And A sub 4 equals permutations. Fixing 4. Okay, so this is my bad stuff. Oh,
You also push a command.
I think I do. We'll do those at 10. Okay. So, all right, so these are my 4 like bad permutations, or bad stuff. And we can look at their sizes. We can look at their the intersections as well. But let's just think about, what is the size of A sub 1? How many permutations of these 4 things fix 1? Okay, so these look like, well, if you had a permutation 1, 2, 3, 4, permutations that fix 1 have to have a 1 in this position. but I can do anything else with these next three. So we can actually just view this as a permutation of the elements 2, 3, and 4 in some order. I can put any of the three here, any of the next two here, any of the next three here. So this should be equal to 3 factorial, right? So a number of ways to rearrange 2, 3, and 4. Similarly, A2, A3, size of A3, and size of A4 also are equal to 3 factorial for the same sort of idea. Now let's look at something that fixes two of these. What about, so A sub 1 intersect A sub 2. What's the size of this? We'll go over here. We have 1, 2, 3, 4. And this is saying, hey, I'm fixing the first two elements. So I have a 1 and a 2, and I can do anything else over here. This is just a permutation of the elements 3 and 4. So this should be either 1, 2, 3, 4, or 1, 2, 4, 3. This ends up being, I'm gonna write this, instead of writing this as 2, I'm gonna write this as 2 factorial, because it's the number of ways to permute this element, this set 3 and 4. Okay, ways to arrange that. And this is true, again, of all the pairwise intersections. All the pairwise intersections, have size 2 factorial. Okay, now let's think about an intersection of size 3, like A1, intersect A2, intersect A3. What's this size? So we're thinking about, okay, I have the set 1, 2, 3, 4, and I'm fixing the first three. So this has to be a 1, this has to be a 2, this has to be a 3. What can I do in the fourth? This is a permutation of a 1-element set. Has to be a 4. This is just 1 factorial, which is 1. And this is true, again, for all of the three-wise intersections, it has to be 1 as well. So for all 1, 2, 3, 1, 2, 4, 1, 3, 4, and 2, 3, 4. All right. Finally, we'll do an intersection of 4. So that'll be A1, intersect A2, intersect A3, intersect A4. What's the size of this? Okay, so we have some permutation over here. 1, 2, 3, 4. And something's in A1, it means it fixes 1. Something's in A2, that means it fixes 2. Something's in A3, it means it fixes 3. And something's in A4, it means it fixes 4. So there's only one way to do that here, which is actually, this is 1 factorial. This ends up being 0 factorial. All the ways to arrange the remaining 0 elements is to do nothing. Okay, so we can figure out what this is. We again have these sort of alternating sums. And I'm going to express this sort of more succinctly using sort of the same idea we had of, actually maybe we'll do that for the next one, but yeah. So the total is going to be the universe, which is 4 factorial, minus what's going on. So we have all of the things of size 1, so this is minus 4 times this. So this is minus 4 times 3 factorial, which is 4 factorial, plus pairwise intersections. So we have 4 choose 2 pairwise intersections. 4 choose 2 pairwise intersections, which are of size 2 factorial. 2 factorial. We have 4 choose 3 three-way intersections. So this should be, sorry, this should have been a minus. Plus the 3-wise intersections, and so this is 4 choose 3 ways to pick 3 of them, times 1 factorial. And then we'll do minus all the ways to pick a 4-ways intersection. So this will be minus 4 choose 4 times 0 factorial. All right, so what is this? This here is equal to 4 factorial minus 4 factorial minus, this is 6 times 2, so that's minus, sorry, the signs cancel, this is plus 12 minus 4 plus 1. So you do this calculation, this ends up being 24, 0, 12, 8, 9 equals 9. Okay. All right, so we've solved these two problems right here using inclusion-exclusion, sort of our smaller forms, and now we're going to use our big one. On this next slide, I'll go small for just a moment. I for real this time. Okay. So we're going to count the derangements of 1, 2, 3 up to n. That is, solve the hat check problem. So hopefully it's clear why, for instance, and I know I'm still small. Hopefully it's clear why this is going to be solving the hat check problem. We can think about the people, the hatted patrons, as being labeled by the numbers 1 up to n. And their hats are given the same labels, and so any sort of permutation is a way to give those things back. For instance, if I have 3 patrons, I'll switch. If I have 3 patrons, I can think about, I'll write them up here. And any way to give the hats back is a rearrangement of here. So for instance, if I have 3, 1, 2, this means patron 1 gets hat 3, patron 2, that 2 gets hat 1, this one right here, and then patron 3 gets hat 2. So this is our connection between this sort of problem and why we might count derangements, these permutations that don't fix any element. All the ways to rearrange something such that no one gets back what they started with is this idea. Okay. So we're going to do so using the inclusion-exclusion principle and using sort of the general form that we've talked about. Okay. So we have a universe of things, which is all of our permutations. And we have things that happen that we want to avoid, which is giving someone back their hat, a permutation that fixes an element. And so our n sub null, n sub naught, is going to be the set of things that don't give someone back their hat, which means it's permutations that don't fix an element. So that'll be what we want to have going on. So I'll write this form again. So keep in mind the following. Right? This is something we remembered. So if we have n sub null is going to be given by this right here. So what is this doing? This is looking over all intersections and is either summing or adding or subtracting them based off if it's an even or odd size set, is all this is saying. Okay. So what I want to do for this is I'm going to set a sub I equals the number of ways to hand back hats such that person I gets their hat back. Hat back. Okay. Right? And I'm going to have this for I equals 1, 2, 3, 4, 5 up to n. So I have n different things. These are the ways to give someone back their hat, or like all the different ways to permute something that gives someone back their hat. Okay. Now what I'm going to do is then for some subset of n, some of the numbers 1 up to n, this intersection right here of a sub i's, which sort of shows up in this setting. This is the set of permutations, the set of permutations that fix all elements of S. And possibly more elements. But what does this mean? This means that, okay, so this is like, for instance, maybe S equals the set 1, 2, 4. Then this intersection right here of I in S of a sub I. This is indicating a sub 1 intersect a sub 2 intersect a sub 4 for this specific S. What does this mean in words? This is the number of permutations that fix 1 and fix 2, or the set of permutations that fix 1 and fix 2 and fix 4, for example. So that's what's going on with this. And so certainly in this setting, n sub naught is going to be given by this value right here. N sub naught is the number of things that don't fix, or number of permutations that don't fix any of my hats. And so that's what we're looking for right here. Okay, so by the inclusion-exclusion principle, we're going to have this form right here. But I'm again going to do this translation. Instead of summing over all subsets, I'm going to go over the size of things. Because the first thing I want to notice is the following. For a general S, I'm going to ignore this example right here. Move out of this. This was just some example. Going back to this case, with a general S, I want to ask the question, how many permutations fix S? Some general set right here. Okay, well, I know where each of these elements in my set S have to go, but the other n minus the size of S elements can go anywhere. They can be set to anything. So this thing right here, it should be n minus the size of S quantity factorial. And the idea is for all the things that aren't in S, I can send anywhere not in S. Everything that's in S has to be fixed, so I have to determine what those things can be. Okay, so I know what this is right here, and I could plug that in for each of these like intersections right here. But then you'll notice that if we have n sub naught equals the sum over all subsets of n of -1 to the size of S over these intersections, this intersection right here, a sub I is equal to, using this substitution for the number of intersections here, or number of permutations, this should be sum over S in n, -1 to the size of S times n minus the size of S factorial. And so like our previous problem where we counted the number of surjective functions, we noticed that this right here, this formula depends only on the size of S. So if we do that, we can re-index our problem where we sum just over sizes of these sets n. So the first thing I have to do is ask myself, how many possible sets of size S are there for my n set? So how many sets of size sets, K can I pick from my patrons? I'm asking how many sets n can I pick from this set n right here, set 1 up to n. This will be size of the number of patrons, so this is n, choose the size of the set. There's n, choose k of those. Many, and really what this is, many sets S contained in the set 1 up to n of size k. So I'm going to erase here. We're on this home stretch. We have number in this empty set should be equal to this piece right here. I'm just going to write it again. The sum over these, each set, -1 to the size of S times n minus the size of S factorial. But we can rewrite this as the index over the size of the set, where we count the number of sets of each size and multiply it by the contribution of each of them, using our same trick. So we have n sub empty is the sum from k equals 0 up to n of -1 to the k times n choose k. This is the number of sets of each size times the contribution of each one of those, which is n minus k factorial. All right, so we have this written right here. I'm going to write this slightly differently now, doing a little bit of erasing. This is, to some extent, the final answer. This is, we've come to our capstone. This is the number we care about. But I'm going to write it, also, we have n sub empty. I don't have a good way to phrase this. I only read it in a book. You ever hear someone like pronounces a word wrong and you laugh at them, but it's because they read it in a book? That sucks, and that's how I feel today. But it's a marathon. All right, so we have this here, should be equal to the sum from k equals 0 up to n of -1 to the k. I'm going to take this binomial coefficient here, and using an earlier theorem, I'm going to write it as a ratio of other other factorials. I'm going to write this as n factorial up top over k factorial times n minus k factorial. Then I have this n minus k right here times n minus k factorial. I have an n minus k factorial in the numerator and in the denominator. So those are going to cancel. I can write this as the sum from k equals 0 to n. Actually, I'll write this as -1 to the k times n factorial over k factorial. And here I'm varying k, but n doesn't change. I can pull it outside the summation. I can write this as n factorial times the sum from k equals 0 up to n of -1 to the k over k factorial. All right. Is this interesting? Maybe. Let me look at this right here. So this is the number of derangements. This is the number of derangements right here. Number of derangements. Okay. Now, as it turns out, this will be a number that's less than 1 as you do this, right? Because how many total total permutations are there? There's n factorial total permutations. So if you want to figure out what fraction of all permutations are derangements, we can write that. Q. What fraction of all permutations are these special things derangements? Are derangements. It should be the number of derangements given here divided by the number of all permutations. So it should be equal to n factorial times the sum from k equals 0 up to n of -1 to the k over k factorial divided by the number of permutations, which is n factorial. That was an n factorial there. And here we have an n factorial in the numerator and an n factorial in the denominator. So we can cancel those out, and you get the sum from k equals 0 up to n of -1 to the k over k factorial. All right, and is this special? Maybe it is. I teach Calc 2 right now. Tomorrow in my class, we start sequences and series. So maybe it isn't special till then, but this is actually the first, n+1 terms of a, Taylor series of e to the power of -1. So this is actually, this very rapidly approaches 1 over e, Euler's number, a special number, I think that has come up before. And it comes up, so this alternation, and it approaches this about as fast as you would think this would approach something. So this does so very, very quickly. Yeah, cool. So this is our last thing that we have. This is the capstone of inclusion-exclusion. I'd like to take a 2 to 3 minute break to do some push-ups. Yeah, but I'll be back soon after paying my penance. Okay.